Hello, welcome to this lesson on drawing covalent Lewis structures. I'm going to start you off by having you draw the Bohr model and the Lewis structure for oxygen. And I want you to describe how they're different. And then which diagram, Bohr or Lewis, do you think would be best for drawing a water molecule? And then explain why. Here we have the definition of a Lewis structure. We've done some of these early on. We did them for atoms, just drawing the Lewis dot diagram for atoms. And we've done a little bit of this with ionic compounds, but now we're moving into covalent compounds. And this is where things get fun. So a Lewis structure is going to show an element's symbol with just its valence electrons. Electrons that are shared are going to be drawn as lines, and electrons that are unshared are going to be drawn as dots. So here we have a nitrogen molecule. This is N2, the primary component of our atmosphere. And nitrogen started out, if you look at the periodic table, it's in group 15. She started out with 5 valence electrons. So it's easy to see that she has these 2. And then she has 1, 2, 3 that are going to be shared with this nitrogen. And this nitrogen over here should also have 5 valence electrons. We have these 2 and then 3 that nitrogen puts into the bond. This is a triple bond. Then over here we have methane or carbon bonded to 3 hydrogens. Carbon is a member of group 14, started out with 4 valence electrons and shares all 4 of them, each with 1 hydrogen, who has 1 valence electron as a member of group 1 and shares its only electron with carbon. It'll get clearer. Just keep with me. You should remember that all elements on the periodic table are going to bond to get a full valence shell, which usually means 8 valence electrons. But when we have nonmetals going out looking for electrons, sometimes they will get those electrons from metals entirely. They get to keep them. And other times when they bond to nonmetals, they have to share. So we're going to look at 2 chlorines that are going to share electrons. So if you find chlorine on the periodic table, chlorine is a member of group 17, meaning it has 7 valence electrons. If we were to draw the atomic Lewis structure for chlorine, it would look like this. Chlorine and 7 dots for 7 valence electrons. Well, this chlorine also has 7 dots and 7 valence electrons. So when chlorine goes out into the world to bond, looking to get a full octet, they kind of like look to each other and go, hey, I have 7 electrons and you have 7 electrons too. Is there any way that I could have an electron? You have a lot. Can I have one? And the other chlorine will say, absolutely not. I'm looking to get 8. I can't give you any because I'm looking to gain. There's no way. So they compromise and they share. So kind of what happens is that they each share 1 electron. I like to use the line, I'll share 1 with you if you share 1 with me. And that's kind of what these chlorines do. So those electrons they each share are going to be put together into a line. The dots get converted into a line. And that is going to represent a single bond. A single bond has 2 electrons in it, 1 from each atom. So you can see that chlorine is going to keep the other 6 electrons and add 1 electron to the bond. This chlorine also going to keep the 6 extra dots and put 1 into the bond. So if we look at it this way, chlorine has 6, shares 7, and is shared the 8th. So there's 2 electrons in this bond. Sometimes these electrons are with chlorine. Other times these electrons are with the chlorine on the left. They share. Now, sometimes our atoms say, I'll share 2 with you if you share 2 with me. And that's called a double bond. In this case, we have oxygen, 2 oxygens, O2, the oxygen we breathe, and it has 6 valence electrons. Each oxygen is looking to gain 2 valence electrons. So this oxygen on the left says to the oxygen on the right, I'll share 2 with you if you share 2 with me. 6 plus 2 is 8. That's how they'll get their 8 valence electrons. So a bond is going to be formed between these 2 electrons, and a bond is going to be formed between those 2 electrons. And those electrons are, the dots get converted into lines once they're shared. So in this case, oxygen kind of just like shifts around these extra dots, has 4 that it's not sharing. It keeps 4 to itself. It puts 2 into the bond, and then 2 are shared with it. And the same happens here. Oxygen keeps its 4 extra dots, puts 2 electrons in the bond, and has 2 electrons shared with it. I'll share 2 with you if you share 2 with me. This is a double bond, which in total is 4 electrons, 2 from me and 2 from you. And now we're up to the triple bond. We're back to nitrogen. Nitrogen has 5 valence electrons. So it's going to say to the other nitrogen, I'll share 3 with you if you share 3 with me, because 5 plus 3 is 8. So we will have nitrogen keeps its 2 extra electrons. And then of the remaining 5, it puts 3 into the bond. It says, I'll share 3 with you if you share 3 with me. So if you could put an imaginary line down this triple bond, half of those electrons belong to the right nitrogen and half of them belong to the left nitrogen. And in total, everyone's going to have 8 valence electrons, because this triple bond in total is 6 electrons, 3 from one nitrogen and 3 from the other, totaling 6, plus the 2 that nitrogen keeps to itself. So that is a triple bond. Now, we don't have atoms share 4 electrons with other atoms. It just gets too crowded. It's not really possible. If you think back here to the triple bond, we have 6 electrons in a very tight space. 8 electrons in a tight space is simply not going to happen. So carbon gets an entire branch of chemistry all to itself of it sharing electrons with other atoms. And that's called organic chemistry. Here, carbon has 4 valence electrons. It's going to share all 4 of them, but it can't share all 4 to the same atom. It's just not possible. Too crowded. So in this case, carbon is going to split up its 4. It's going to share with this hydrogen and that hydrogen and that hydrogen and that hydrogen, and it is going to make 4 single bonds in order to get a full valence shell, sharing multiple places. So carbon has 4 electrons and has 4 shared with it, totaling 8. Now, hydrogen is a little bit weird because hydrogen can't even hold 8 valence electrons. It's way too tight. Not enough space for all of those electrons. Not enough protons to even hold them together. So hydrogen is going to follow the duet rule. Remember, all of the atoms want to look like noble gases. In this case, hydrogen is going to want to look like helium with just 2 valence electrons. So hydrogen has its 1 valence electron. It only needs 1 more to look like helium. So it says to carbon, I'll share 1 with you if you share 1 with me. And carbon says, yeah, that's cool, but I got to share some other electrons with other hydrogens. And this hydrogen's like, yeah, of course, I don't care. Do what you got to do with your electrons. I just need to worry about me. So that's what's happening here. Notice that there's no dots on this Lewis structure at all, and that's because there are no leftover electrons for an atom to hold on to all by itself. It's sharing everything it's got. So here in summary, we have the type of bond, the number of lines, and the number of valence electrons. Remember, each line represents a pair of shared electrons. In a single bond, the atoms say to each other, I'll share 1 with you if you share 1 with me. So it's a single bond because they put in 1 electron, but they get 2. Sometimes they get their own, and sometimes they get the one that's been shared with them. So the double bond, you put 2 in, but you can have up to 4. And then the triple bond, you put in 3. I'll share 3 with you if you share 3 with me. So there's 6 in total. Drawing Lewis structures can get really complex, especially if you're going to start talking about formal charges and resonance, which I'm not getting into here. I am looking to show you how to draw binary covalent Lewis structures, stuff that's pretty simple, just like 2 elements at a time. When we get into organic Lewis structures, it's going to be a little bit more complex, but that naming system lends itself to drawing beautiful Lewis structures that are actually really easy to figure out. But until we get there, we will not be talking formal charge and resonance. If you're looking for that, I'm sorry, you're going to have to go find another video. I don't like resonance. I think it's such a pain in the neck, and I don't want to teach it, so I'm not going to. I'm just trying to get the basics across here. So when we're drawing inorganic binary Lewis structures, we are going to determine the number of valence electrons for each atom. You just do that using the periodic table. Remember, everything that's in group 14 has 4 valence electrons, 15 has 5, 16 has 6, 17 has 7, 18 has 8, but we're not bonding with them because they already have a full valence shell. Then what we're going to do is take those valence electrons and draw them as dots around the element symbol. Think back to when we were doing atomic Lewis structures. We're going to start really with that. Then I recommend with a pencil, you just start connecting these dots until you get all of the atoms having a full valence shell. It gets easier with time. You will figure it out. Most of the time in a chemical formula, and I should specifically reiterate, most of the time in a chemical formula, the element that comes first is going to be the central atom, and then you'll have whatever is second is going to be attached to the sides, kind of like we had with methane with the carbon in the middle and the hydrogens around. The formula there is CH4. It kind of tells you that C is in the middle. That happens most of the time. And also make a note to look out for small elements like hydrogen. They only want 2 valence electrons. They cannot possibly fit 8 valence electrons. And then remember that each atom is going to say to the other, I'll share 1 with you if you share 1 with me. I'll share 2 with you if you share 2 with me. That's the only way that we're bonding right now. There is something called a coordinate covalent bond where one atom does all the sharing and the other atom does not. We're not talking that here. In this case, in this video, in high school level chemistry, we are talking about fair sharing. I'll share 1 with you if you share 1 with me. Now, we are going to take the bonded electrons that they decide to share, and they are going to be converted into lines. So every 2 electrons that are shared, 1 with you, 1 with me, those are going to be converted into lines. They are no longer dots. Now, Lewis structures are going to show you how electrons are shared among the atoms, but it does not show you what an atom would look like, or what a molecule rather would look like in real life or in 3 dimensions. So we do not consider Lewis structures to be real life representations. They're just models. This is going to be important, again, when we talk about intermolecular forces. And specifically, it's going to be really important when we talk about water. Water is a polar molecule, which means that it kind of acts like a little magnet. We'll get to that later. You can draw a Lewis structure for water that makes it look like it's not a polar molecule, and that Lewis structure would be correct, technically. So I, from the inception of Lewis structures, have my students draw water at a right angle. So we're going to draw water and all of its cousins at a right angle. Now, the reason H2S and H2SE are considered water's cousins is because if you find oxygen on the periodic table, sulfur is right below it, selenium is right below that. When you have this type of water molecule, or this type of molecule that kind of looks like water, it's a cousin to water, we're going to draw it at a right angle. This is going to be a closer representation to the real life picture of water, and it's going to help you later. So this is just something that I recommend that you memorize. You can technically draw the Lewis structure for water in a straight line, hydrogen, oxygen, and then another hydrogen. I don't want you to do that because it will lead you to the wrong answer later. Draw water and its cousins at a right angle. Now, secondly, anytime we have double bonds, this is going to be true later when we get to organic. Double bonds have to go in a straight line. They cannot bend. The reason for this is because these double bonds represent 4 electrons, and they are going to be repelling each other. And the more spaced out they can be, the happier they'll be. So for realsies, double bonds cannot bend like water does into the right angle. It's not going to happen. So if you have a double bond, draw it as a straight line. Just get in that habit now. It will help you later. Like I was saying before, in a chemical formula, a lot of the time the element that's listed first is going to be drawn in the center. But another way that you can more or less figure out how the drawing is supposed to look is that the atom with the lower electronegativity is typically going to be in the middle. Now, if you look up the electronegativities of all of the elements, carbon has a lower electronegativity than oxygen. You can also figure this out using your periodic table trends if you don't have the exact numbers. Oxygen is closer to fluorine on the periodic table than carbon is. Carbon is further away, so it's going to have a lower electronegativity. Usually the thing with the lower electronegativity is going to wind up in the middle. In the case of carbon dioxide, the formula for that is also true, where the carbon comes first, and that's going to be the atom in the middle. Again, this is not a 100% blanket statement rule. It's just something that can help you get started with your picture. Sometimes it's not true, and your picture is going to look weird and it's not going to work, and then you'll just have to know, okay, this must be one of the exceptions to that center atom rule. This is going to lead into, again, intermolecular forces in a few videos, but when we have an atom that has multiple lone pairs of electrons, meaning it has pairs of leftover electrons that it did not bond with, those are actually going to need a little bit more space, and truthfully, they should wind up next to each other. That's going to make your molecule lopsided, and that is going to make water polar. Like I said before, it's going to act like a little magnet. So right here, I have a model of a water molecule. Really, my water molecule is supposed to look like this. I'm supposed to use a red for oxygen and then these for hydrogen. But just for the sake of this description, I did it on a carbon just because it bonds in 4 places and I wanted you to see it. These little flags or bunny ears represent these leftover electrons. And you can see that they kind of want their own space, right? Electrons don't want to be near each other. At the same time, these hydrogens don't really want to be near each other. So this in 3 dimensions kind of looks like a tripod. And you'll have just one thing like sticking up off the top. There you have it again. And this, no matter how you orient it, if I were to like pop off a hydrogen and pop off this lone pair and then rearrange it, no matter how I arrange it, the bunny ears or the extra leftover electrons are always going to wind up next to each other. So when you draw the picture, it's a good idea to just kind of oriented at the right angle. It's not quite a right angle. Water's angle is actually like 104.5, I think it is. It's a little bit bigger than a right angle, but just getting in that habit is going to help you. Now, again, Lewis structures don't show you the real life picture. Lewis structures are going to show you how electrons are being shared. The real life picture looks more like this. And the way I'm kind of having you draw this is like this. So you have hydrogen, oxygen, hydrogen, and then these bunny ears are actually like in the same plane of space. So you can't actually, if you're looking at the Lewis structure, you can't see 2 things at the same time. If you want to put your bunny ears at a right angle instead, your hydrogens are going to be in the same plane and one's going to block the other. You see that? One of them just disappeared. So again, your Lewis structure is not here to show you what it looks like in 3 dimensions. It's just to show you how atoms bond. But if you draw it at this right angle, you are going to prepare yourself later on for the fact that this molecule is very negative in this area where the extra electrons are. Because electrons are negative, you got a big cloud of negativity over here. And then with these hydrogens, you actually have a big cloud of positivity. And this is going to show you that the molecule is lopsided. So again, please draw your water molecules at a right angle. So that is it on Lewis structures. There are a few that I recommend that you memorize just because it doesn't make sense to use them over and over again. And those are really the ones that I've showed you in this video. You have water that I think you should memorize. Carbon dioxide is one of those. H2S and H2SE, I think, are worthwhile to memorize. Then we have methane, CH4 is a great one. Nitrogen, oxygen with the double bonds. I also think that all of the halogens are worthwhile to memorize because all of the halogens have 7 valence electrons. You can plug in any halogen in place right here and it would have the same Lewis structure. So you don't have to sit and memorize fluorine, chlorine, bromine, and iodine. Just remember one of them as the halogen Lewis structure. These are the things that are going to come up a lot of the time. And then once you have this as your ground layer foundation for Lewis structures, it's going to be a lot easier to draw some of the crazier things. Best of luck with drawing your Lewis structures. Please leave any questions you have in the comment section below the video. Subscribe so you don't miss the next lesson, and I'll see you there. Bye.